Hey everyone, my name's James and I'm joined today by Tristan, and today we're going to be talking about the question, is fusion power viable? I'm going to begin with a brief introduction to what fusion power is and how we achieve it, and I'm going to discuss some of the major challenges that fusion power faces on its route to becoming a commercially viable energy source. We'll also discuss how some of these challenges are going to be, or potentially maybe solved, and we'll discuss some of the social and economic issues surrounding fusion energy and fusion's place on the global energy landscape. So I'm going to begin by talking about fusion. So essentially, when fusion happens when two light atoms like hydrogen collide at extremely high energies, and their nuclei can fuse together. And when this happens, vast amounts of energy are released. Much more energy than just burning the hydrogen in the presence of oxygen. There's one particular fusion reaction that we are hoping to exploit in a commercial fusion power station, and that's deuterium and tritium, the DT reaction, which you can see on the screen here. It's essentially two isotopes of hydrogen coming together to form helium. But there are many different types of fusion reactions, and there are trillions of natural fusion reactions taking place right now in the center of stars like our sun. And nearly all of the natural light in our universe ultimately arises from fusion. A power station based on fusion is a very attractive prospect. Unlike other forms of energy, it's inherently safe. There's no chance of a runaway reaction or any kind of radiological release, or it's much less likely to have a harmful radiological release. It's extremely low carbon, directly produces no carbon at all, and it could potentially meet our global clean energy demands for millennia, because at least one of the fuels, deuterium, is widely present in our environment and can be easily extracted. So in order to get fusion to happen, we need a special device called a tokamak. And one of the reasons is the extremely high temperatures involved. Positively charged nuclei repel one another. So in order to get them to collide, they have to be moving extremely fast. And when we're talking about gases, this speed is proportional to temperature. Now, the temperatures involved are frankly mind-boggling. We're talking sort of 150 to 300 million degrees Celsius, which is actually one of the hottest things in the universe. And at these temperatures, the gases turn into plasmas, which all you need to know about a plasma is essentially it's a conductive gas that can be manipulated or moved around by magnets. And this is how a tokamak works. It uses very strong magnets to confine an extremely hot plasma of hydrogen, which allows it to be heated up to extremely high temperatures. If you didn't have these magnets, the plasma would just come into contact with the walls and it would lose all of its heat, and therefore you wouldn't get hot enough to achieve fusion. So a tokamak is a device in which we try to make fusion happen. So if we know how fusion works, and if we have a device that does it, then why do we not have fusion? And it's because there's a couple of major technical challenges that we still haven't solved. So I'm going to talk about three of these challenges and how we hope to solve them. So challenge number one is troublesome tritium. So I mentioned that deuterium is widely abundant in our environment and we're able to extract it and use it. But the other fuel that we need for the deuterium-tritium reaction is much harder to produce, and it's very rarely found naturally on Earth. In fact, there's only about 20 kilograms of tritium produced globally every year, and a single fusion power station might need as much as 200 kilograms. We're building a massive tokamak in the south of France, and this is called ITER, and ITER will actually use up the world's stockpile of tritium. It's a huge project. Governments all around the world are coming together to try to solve the problems of fusion. But essentially, once this stockpile of tritium is gone, we're in trouble. So for fusion to become a reality, we need to find a reliable supply of tritium. Challenge number two is all about the plasma exhaust. So I mentioned that fusion with a DT reaction, you have two hydrogen isotopes of hydrogen that come together and fuse to form helium. Now, the helium that's produced is actually an impurity, and in order to keep the fusion reaction going and to keep the plasma burning, we have to remove this impurity. And this means that we have to have contact somewhere between the plasma, which is at millions of degrees C, and the walls of the tokamak, which is at about 400 degrees C. And this means that the plasma-facing surfaces of the tokamak, where it comes into contact with the plasma, have to be able to withstand incredible heat loads. And these heat loads are actually 10 times greater than those experienced by a spacecraft during re-entry. Now, we have a lot of very good high temperature materials that you can see in this picture here. But the thing is, a spacecraft only really needs to land once, or if you're SpaceX, a couple of times, whereas a fusion reactor needs to operate reliably for about 20 years. So we need very high temperature materials that are extremely reliable and behave in predictable ways. Challenge number 3 is all about the plasma itself. So fusion plasmas are magnetic and they're charged and they're extremely hot. And what this means is that very, very small changes in density or electric field or temperature can rapidly propagate and lead to instabilities that cause the plasma to become unstable. When this happens, if these instabilities are serious enough, the plasma can come into contact with the walls of the tokamak, which you can see on the pictures on the left and right of the screen. This results in damage, which you can see in the middle of the screen. When we're talking about a commercial power station, this level of damage is completely unacceptable. So we need to find better ways of confining the plasma and making sure that these kind of events are vanishingly rare. So these are the 3 major challenges of fusion. I'm now going to talk about some of the solutions. Solution number 1 is all about tritium. So tritium breeding blankets is the idea that we can produce tritium itself inside the fusion reactor by using the neutron that's produced from the deuterium-tritium reaction to split lithium-7. So lithium-7 is an isotope of lithium, and it has a special property that when it's hit with a high-energy neutron, it can produce tritium and helium. So the idea of a tritium breeding blanket is that we wrap the walls of the tokamak in a blanket of lithium-7, and hence we can sort of produce tritium that we can extract and refine and then pump back into the tokamak to keep the reaction going. I'm now going to pass over to Tristan, who's going to talk to you about high heat flux materials.
So James has talked about the heat fluxes that are going to affect the first wall. And as you can see here, they're up to 20 megawatt per square meters. And if you don't understand this figure, it's about 500,000 light bulbs only flashing into a square meter. And this is enough to melt a ton of steel in less than a minute. So we need to make sure that we come up with designs for the first wall, which is able to extract the heat and flush it away in other parts of the reactor. And for that, we're using complex designs and also good materials, such as tungsten and barium, which are going to be facing directly the plasma. And those materials are used because they've got a very, very high melting temperature. In addition to those, we use also materials such as copper, which is known to be very thermally conductive, and also steel, special kind of steels like urethane, which allow to build the structure of the reactor. And as you can see in the slide, the 2 bottom pictures describe the first wall of the reactor, which is being built in the south of France, which is ITER. And on the top right, you can see a more detailed design where tungsten, steel, and copper are assembled together to produce first wall, which is again able to extract the heat very quickly and allow the materials inside the reactor not to melt. Another solution to the technical challenges we've been discussing is the superconductive magnets, which are used to create the plasma confinement and avoid any collision between the hot plasma and the wall of the tokamak. So over the years, we've been using different technologies, and the first international tokamak jet, which was built in 1982, was using non-superconductive magnets, which were copper. And they were able to reach relatively high confinement pressure on the plasma. However, because of copper not being superconductive, those magnets would heat up very, very quickly. And this is a problem to sustain fusion reactions for a very long time. So in ITER, the next fusion reactor, we're planning to use superconductive magnets, which below certain temperature don't heat up and can be conductive without heating up for very long duration of times. And they also allow to reach higher plasma confinement with, for instance, here 11.8 Tesla. And in the future, for the first commercially viable reactor, which we'll probably name demo for demonstration reactor, we plan to use high temperature magnets, which have higher critical temperatures of about 40 Kelvin, which is still pretty low, but way higher than what ITER will have, and probably will be able to produce confinement, a plasma confinement, which will be twice as strong as ITER. So we've got a lot of merits here to develop the superconductive magnets, which are stronger magnetic field, which allows you to build smaller and more efficient reactor. It also allows you to have less cooling, which means that the efficiency of the reactor will be better, and also to better control the plasma by having the separation distance between the wall and the plasma the largest as possible. So now that we've discussed about the challenges and also the possible solutions that are being developed right now, we need to put fusion in context. And the question is now, is there a right place for fusion in the energy future of the planet? So first we can take a look at economic cost. How does fusion compare with other energy sources? And as you can see from the first two lines, the current electricity market price is actually very low. It's about 40 to 50 pounds per megawatt hour. And it is estimated that fusion electricity will first come at a very, very high price, meaning that if you only rely on those figures, fusion is really not viable at all. But remember, we've got to put the energy systems in a wider context. We've got to consider other parameters, such as the social cost of carbon. Now with climate change, we need to avoid emissions from fossil fuels, for instance. We also need to consider the fuel security, the storage requirements, and the available resources, because some resources, such as, again, the fossil fuels, are unlimited, and other points such as recyclability of materials, power density, water requirements, and pollution. But those, and there are many, many more that you should consider when you decide to build an energy system. And in the next few slides, we're not going to discuss all of them, but I'm going to focus on two, which are going to be power density and also the available resources that we have at our disposal to build machines and to make them run. So power density. Here, I'd like to introduce you to a very famous book about energy, which was written by David McKay, a professor in Cambridge, and it's called Sustainable Energy Without the Hot Air. And in this book, David McKay is exploring the different energy sources and using relevant physical figures to compare the different energies and basically to imagine a future where we would be running on energy with low carbon emissions. One of the key graphs of this book is the graph presented on the left, where on the y-axis you can see the energy consumption per person given in kilowatt-hour per day per person, and on the bottom axis you can see the population densities of countries. And as you can see, countries are widely spread in this graph. The least developed countries tend to be located at the bottom left. However, the more developed the country, the more you can see it on the top right of the country. You can, for instance, note countries like Hong Kong, Singapore, or even the UK that have got a high necessity to have high power density to power the needs of the people. And what this graph shows is if you need high power densities, you need to rely on energy sources that can provide those. And fusion is actually a good source of that because it's a conventional power plant and it will be able to deliver about 1,000 watts per square meter of power density, which is way higher than some energy sources such as energy crops that only yield 0.5 watt per square meter in the UK. So those are figures that we need to take into consideration to answer the question, is fusion viable? The second aspect I'd like to discuss is the resources that we have available. So on the right-hand side, you can see a graph where you've got the available resources that we have to produce energy. On the right side of the graph, you can see the metal and different fossil fuels, and you can see that those are unfortunately limited, meaning that in the future, we might either run out of them, or it would be harder and harder to extract them from the ground to use them. Then what do we have left? We've got left the renewables and the sun. And as you can see, our world uses a lot of energy. And what I mean a lot is considerable. On the bottom right, you've got the different figures of the world energy consumption, and you can see an increase from 2000 to 2020 of about 50%. And by 2050, it will be possible that we might add another 50%. And at that point, it might be really, really tricky to get all the energy we want for our societies only based on the renewables that we have at our disposition. And this is not only half of the problem, because we probably need to consider as well CO2 emissions, as I mentioned earlier, but also what about the metal resources? Have we got enough metal resources to build the energy future that we want? And in this sense, fusion is a very, very compact way to produce energy with low metal requirements, and also terrestrial reserves of lithium that exceed 1,000 years old. 1,000 years, sorry. So I've discussed two of those factors, and now it's time to conclude a bit about fusion. Where are we? As you can see on the right graph, until the year 2000, there was a very, very rapid progress of the triple product, which is how close we are to getting fusion. And the trend was actually exponential, because this graph is a logarithmic graph. But from 2000, we've seen a bit of a slowdown, but we're very, very close to prove that fusion energy is viable. Most people think it's always 30 years away, but now politicians, such as Boris Johnson, say that we're on the verge of nuclear fusion. ITER will probably have its first plasma in 2025, and with the development of small compact tokamak, such as STEP and mass upgrade in UK, we can expect to become even closer to nuclear fusion in the next few years. To put this into context, our world is consuming more and more energy each day. And in the context of climate change, we need, on the left graph, to phase out fossil fuels such as coal, oil, and gas, which means that they need to be replaced by fusion, by something else. And actually, fusion could be the energy source to compensate for this gap of fossil fuels energy. Thank you for listening, and now we'll take a few questions from the chat.